going to continue with Gauss's law. So this is something that allows you to calculate the electric field due to some charge distribution. Okay? And this is, in that sense, and in other senses as well, equivalent to Coulomb's law. And this requires you to define the concept of electric flux. So, electric flux. Now, we define this for a uniform electric field as E dot A, and this A was some area times some normal vector. Okay? And for an arbitrary surface, this normal vector was a bit ambiguous. You could choose two sides, but it turns out for Gauss's law, we always deal with closed surfaces where inside and outside is unambiguous, and so there's no ambiguity in choosing this one. This is always going to be chosen outwards. Right? So this is for a uniform electric field, and for where this is constant, so it's for a flat surface. And if you have some non-uniform electric field or a complicated surface, you need to go to an integral. So this is going to be somewhat like this. Okay? So this indicates a closed surface. Okay? And Gauss's law states that this total electric flux through a closed surface is going to be Q enclosed divided by epsilon naught. And as I tried to emphasize before, this electric field is the electric field on the surface, on the points on the surface, but it's the electric field due to everything. It's just the electric field in the universe, right, at those points. This, on the other hand, is just the enclosed charges. So you have some closed surface. Inside this, there are some charges. You add these up, just, like a scalar sum, no problem. And this gives you the enclosed field, whereas the electric field, for example, at this point, is going to have contributions from all over. Right? These charges are also going to contribute to the electric field, not just the ones inside. This is something that sometimes confuses people. It goes away with practice, but it's best to not get confused at the very beginning either. Yeah. Now, as I said, this is a very complicated, nasty integral, and the trick is you don't take the integral. Right? So you don't want to take the integral. What you want to do is to avoid this. And the first thing to do is to get rid of this dot product, and then try to take the electric field out, and then the rest is going to be a simple area calculation. Right? You have some spherical surface, maybe part of it, you have some rectangular surface, something like that, or cylindrical, and you're going to take this out. Now, how do you do this? How do you get rid of the dot product, and how do you take this electric field out? Well, the dot product is special when the two vectors are orthogonal, or when they're parallel and anti-parallel. Right? If they're orthogonal, if they're perpendicular to each other, the dot product vanishes. If they are anti-parallel to each other, it's just their product with a negative sign. If they are parallel, it's just their product without a negative sign. Okay? So we'll try to find this kind of situations. So you have some freedom in choosing this Gaussian surface, and we're going to exploit that freedom. We're going to make this dot product simple. You're also going to have some simple expressions for your electric field. Ideally, it's going to be constant or zero, something like that. But if it's something simple enough, then we can still take the integral. Right? But the first issue is to get rid of the dot product. And then the integral is going to be very simple. It's not going to be an integral at all. And you can equate it to two sides, and you can solve for your electric field. Now, to do this, to be able to exploit this property, to get rid of the dot product and everything, you need to use symmetry. Okay? And I'm going to use some part from another book. So this is from Knight's book. I already given you some excerpt from this in Optic class. Now, this is a nice explanation of symmetry. There is also an explanation of symmetry in Giancoli in your book. I'm using this not only because I like this better, but also it's good to have some variety. Okay? I'm not saying you should not read the book, just read this one. On the contrary, you should read both. Right? This is an important and potentially confusing concept, so it's best if you use multiple resources. Okay, so what does this tell you? So there are something. So there are kinds of symmetry. So symmetry in physics, it's a different meaning than what we use symmetry in everyday life. So symmetry in everyday life usually corresponds to mirror symmetry. The left is the same as right. But symmetry in physics means that you make a transformation, you change the system in some way, but there is no physical change. Everything that you're interested in remains the same. Okay? Now, how can you change the system? There are three things you can do. You can translate, so you can move the charge or your system along an axis. Or you can rotate, so you can just turn things around a given axis or a pivot point, something like that, and you can reflect this. Okay? Again, you take some point or some line or some plane, and you reflect everything around these objects. And so when you change these things, if there is no change in your physical system, you talk about the translational, rotational, reflectional symmetry. Okay? So there are some charge distributions that show multiple of these. So for example, if you have a charge, an infinite cylinder of charge, like over here, so you have something, sorry, let me just find this. Oh, this one, yeah. So like over here, then you can translate parallel to the axis, okay, regardless of where you are in space, as if this is an infinite center of charge, when you're moving along a line that's parallel to its axis, nothing is going to change, right? The universe that you see is going to remain perfectly the same. You can also rotate around the axis, and again, nothing is going to change. Now, remember, it's an infinite cylinder, so as you're rotating around the axis, you keep your distance from its center, or the central axis line, the same. And if you do this, you're not going to see anything. It's uniformly charged, it's just an infinite center of charge. You can also have a reflection in a plane containing the axis. Right? So if you just imagine a plane that's passing through the axis, here it is drawn in a particular way, but this can obviously be rotated continuously around 360 degrees, 180 degrees, because after that it just coincides itself. But any reflections with respect to this plane is going to leave things the same. So let's say that I'm at a point, 5 meters away on this side of the plane. If I move 5 meters away to the other side of the plane, the universe I'm observing is going to remain the same. Everything is going to remain the same for me. And likewise for reflection perpendicular to the axis. Imagine that I'm starting 3 meters to the left of this plane that's perpendicular to the axis. If I now move 3 meters to the right of this plane, everything should remain the same. Okay? It's similar to, so this one is similar to the translation parallel to the axis, but it's not the same. Okay? In this case, they just happen to, the electric field that you see is going to be just constant. So doing a translation or reflection is not going to change anything. You always get the same thing, but not necessarily for other situations. And likewise, the rotation and the reflection in plane containing the axis is going to look similar, but they are not exactly the same. Okay? So for this particular simple charge distribution, they just happen to give very similar answers. Right? Now, do you have any questions about these? So this is potentially something nobody has seen in high school. So it's usually those things are a little bit more difficult to grasp. Are there any questions? So can you see my screen? Is that like I'm sharing the screen in somewhat unconventional way, but I'm guessing. Okay. So are there any questions? Anything? All right. So let's see if we, how we use this symmetry. Now, the question here is that you have some infinite cylinder of charge, and could the field of a cylindrical charge distribution look like this one? Okay. Now the answer here is going to be no. So this is a cylindrical charge. There are these electric field lines coming out, and they are rotationally symmetric around this, but they are tilted one way. Now because we have this reflectional symmetry, reflection perpendicular to the reflection with respect to a plane perpendicular to the axis, we can't have this. Right? So let's imagine a reflection plane here, and reflect everything, all of these, with respect to that. The electric field is going to change. It can't. Because when you do that reflection, the charge distribution did not change. And electric field is determined by the charge distribution. So if you're having something like this, then it's a contradiction. The electric field cannot be like this. Right? or it could be like this. So this is the end view of the cylinder. You're now looking at it from the infinitely thin cylinder from through its symmetry axis, something like that. Again, this is not allowed. This time, because of the reflection in a plane containing the axis. Okay? Now that plane would look like something like this. Right? So this is our symmetry axis, the center of the circle, which is the boundary of the cylinder. So the reflection plane is passing through the center, and it's going in infinite direction into the page and out of the page. And if you reflect this, you're going to get a different electric field. And so this looks like it could be, and in fact, if you're familiar with the magnetic field produced by a current, then this is somewhat similar to that one. But for electrostatics, for electric field, this is not allowed, because when you're reflecting over this plane to the left and to the right of this plane, the charge distribution is not going to change. But if electric field is changing, then you have a contradiction. This cannot work. Okay. Now, I have, and there's some further discussion here that I can share this on AutoClass and you can read this. Now, here are three very nicely drawn pictures. That's why I'm actually switching to sharing files for this lecture rather than trying to draw something on board. I could never draw this, and this illustrates the three kinds of symmetry, or three fundamental symmetries as they put it: the planar symmetry, the cylindrical symmetry, and spherical symmetry. So these are different from the other stuff that we said: rotational symmetry, translational symmetry, and reflectional symmetry. So these include those. So planar symmetry has translational symmetry in two directions, and also has reflectional symmetry with respect to up and down. Okay? Now this could be a little bit more complicated. So here's a more complex example. We have two infinite planes, but they contain opposite charges. Now here, so imagine these two are just cross sections of the two planes. That's extending to infinity. We're just seeing them from one side. Now here we have translational symmetry. So right and left, or into the page, out of the page, as you move along those directions, nothing is going to change because these are infinite planes. But for the reflectional symmetry, it gets a little bit more complicated. As you go from up to down, you expect things to switch. The plus is replaced by minus, and minus is replaced by plus, so you'll expect the electric field to switch directions. Okay? So this is a little bit more complicated. It doesn't remain the same just by reflection. It remains the same by reflection plus a charge conjugation. Right? But you're going to get very familiar with this, and you're not going to have any trouble solving this. Now here we have cylindrical symmetry. We already talked about this. So this has rotational symmetry, it has reflectional symmetry in a multitude of ways, and it has translational symmetry along its axis. The more complicated example here would be coaxial cylinders. Again, these cylinders could be charged, but yeah, again, you're going to learn how to handle these. We're going to look at some examples. And a very, very common one is spherical symmetry. So spherical symmetry, as the name indicates, requires some spherical charge distribution. And this is the simplest one. It's not obvious whether this is a full sphere or just a spherical shell, but it doesn't matter. The charge is uniformly and spherically symmetrically distributed. This is going to have a number of reflectional symmetries along any plane that passes through the center of the sphere. It also has rotational symmetry around any axis that passes through the center of the sphere. It doesn't have any translational symmetry. As you move along the axis, you're going to be changing your distance from the center of the sphere, and in general you would expect your electric field to be different. Here the more complicated example is really not that much more complicated. Concentric spheres, you'll keep your spherical symmetry, and your electric field lines are always going to be in the radial direction. Okay? So here the electric field lines are perpendicular to the plane because of the symmetries of this problem. Here they are perpendicular to the cylinder, but this one has an infinite cylinder, keep that in mind, and here they are perpendicular to the spherical shells that are concentric with the sphere. Okay. Again, these are presented in different ways in Giancoli. I just want to provide an alternative point of view, but you should by all means read both. Okay. Now here's a nice feature of this book, that they have these questions. So here we have a uniform charge rod that has a finite length. So it's not an infinite cylinder, but it still has a number of symmetries. The road is symmetric under rotations about the axis and under reflection any plane containing the axis. It is not symmetric under translations because it's finite. So as you move to this, as you are moving along a line that's parallel to the axis, things are going to change because you are closer or farther from the ends of this road. Okay, so you don't have translational symmetry, but it is rotationally symmetric, and it is reflectionally symmetric with respect to planes passing through the axis. It's also reflectionally symmetric with respect to the plane that bisects the road, right, passing through its center perpendicular to the road. For any other plane, it's not going to be reflectionally symmetric. Like if you have a plane that's passing through here, left is not the same as right because it's a finite road. Now the question is, which field shape or shapes match the symmetry of the road? Alright, so more than half the people have answered. So let me go back to this problem and see if I can demystify it. Now, first of all, this is not asking you about your previous knowledge. Okay? This is to test your knowledge about symmetry. So what we just learned. So and there are some symmetries that this finite road possesses, and you need to figure those out. Okay? And you need to figure out if the electric field obeys those symmetries or not. So first of all, B is out because it doesn't obey reflectional symmetry for a plane that's just bisecting the road. So if you have a plane that's passing through here, perpendicular to the plane of the page, then the left and right should be symmetric because the charge distribution is symmetric. If I exchange left with right, everything remains the same, but the electric field is going to change. So I can't do that. So B is out. B is not possible. Now, if you look at C, the illustration on the left is okay. It obeys all the symmetries that I can think of: up, down, reflectional symmetry, left, right, reflectional symmetry. But if you look at over here, then if I let the plane pass through the center, again perpendicular to the page, and passing through the center of this circle, which is the boundary of the cylinder, then left-right symmetry is not going to be preserved. So C doesn't work either. Now when we look at D, something similar happens. So you might be thinking, okay, first of all, there should be electric fields coming out of here because there are charges, but this is not necessarily so. Okay, this is a finite road. You don't know what kind of cancellations are going to happen. But again, if you let the plane pass through the center of this circle on the right, then reflectional symmetry is going to be violated. The electric field on the left is going up, electric field on the right is going down. So if you flip those, then you're going to change the electric field, not the magnitude perhaps, but the direction, and that's not allowed. Okay? Now with A and D, there is nothing wrong. Okay? So only one of them is physical. D is physical. This is what the electric field of a road would look like. But the electric field given in A is not violating any of the symmetries of the road. If you look at start on the right side, now with the right side there's just one thing or a couple of things you can do. One is rotational symmetry. As you rotate around, this should remain the same. This one evidently does. And the second one is reflectional symmetry, that for planes passing through the center, whatever you draw, as you reflect around those planes, this should remain the same. It does. Okay? So there's nothing wrong here. But for this one, what we can do is we can get up-down symmetry, which is present here, and left-right symmetry, which is also present here. So this is okay. As far as the symmetries of the road goes, this electric field given here obeys them. This also obeys them, but this one is physical one. This one is not physical. Right? You would expect the electric field, not be converging to a point like this, but it would look like that. It's diverging from the road. But as far as symmetries go, both are okay answers. Right? And symmetry is something very, very important, something very powerful that we're going to use again and again. So that's why I wanted to keep this. Now let me do this again. Right, I'm going to go back to my whiteboard and start looking at the examples from the book. But do you have any questions about that finite road? Is there anything? You can hear me, right? They are so silent that I can't even tell.
Yes.
Okay. Okay. Go ahead.
I answered this question first. I thought of this road, if it's finite road, is of spheres that goes inside each other, infinity spheres. So we will have the same
But there are no spheres here, so I'm not sure how.
Yes,
how...
yes. I mean, I assumed like it would be done by spheres.
Mhm.
It's a road, so
Okay.
because
Yes.
road lines, electric field lines going outside of it,
Mhm.
like
You're not wrong.
sun.
Okay, so that is how it would look like, but that's not what the question is asking. The question is asking which of the electric field given is consistent with the symmetry of the road. Now, there are some configurations of electric field that's consistent with the symmetries, but it's not physical. That's not how the electric field of an actual finite road looks like. Okay? So the actual electric field of a finite road would look like what you're describing, but at the same time, that's not what the question is asking. So one of them, the choice A, is not physical, but it's consistent with the symmetries of the rod. But it's not what you would get if you actually think of this as little spheres or point charges or whatever. Does that answer your question?
Yes, yes, thank you.
Okay. Any other questions? Anything else? Okay. So we don't have much time, but I think in 15 minutes we can look at a couple examples at least. So I'm going to start with the simple examples from the book. Again, the solutions or the videos of the solutions for the suggested problems is already on YouTube, so you can check those out. And if you have questions, please feel free to ask them. So the first example is example 3, a spherical conductor. The thin spherical shell of radius R0 possesses a total net charge capital Q that's uniformly distributed on it, and there's a figure. It's fine. Determine the electric field at point A outside the shell, inside the shell. What if the conductor were a solid sphere? Okay. So we have a spherical shell of radius R0, okay? And there's some charge Q distributed on this. This is a conductor, so the charge is just going to distribute itself uniformly. It's a spherical symmetric surface, so the charge is going to be distributed spherically symmetric as well. And they're asking for the electric field outside the shell and inside the shell. Okay? Now, we are going to use Gauss's law, because first this screams Gauss's law, and second, this is the chapter for Gauss's law. So what we're going to do is we're going to do this. Close divided by epsilon naught. And we need to choose a surface. And we want to choose a surface such that we are going to be able to figure out the electric field or the properties of the electric field on that surface easily. Now, because our charge distribution is spherically symmetric, the first thing that should come to your mind is to consider a spherical surface. So let's say that we are looking at a point that's of distance r from the center, and I'm going to choose a surface that passes through that point and is spherical in shape. So in other words, a sphere of radius r. Okay? Now, on that surface, what can I say? Well, the electric field has to be in radial direction because the charge is distributed in a spherically symmetric manner. The electric field should be also spherically symmetric, and the only way that can happen is if it's in the radial direction. So it can be inwards or outwards. Because this is positive charge, it's going to be, in fact, outward. Okay, so I'm going to have E like this, E like this, E like this, and so on and so forth. Okay, everywhere perpendicular to the surface. So again, keep in mind that this is in fact a three-dimensional surface. I'm just drawing a cross-section here. Now on top of that, I'm going to have, and this electric field, because it's equidistant from the charge distribution as I go around on this hypothetical Gaussian surface, my distance from the charge distribution does not change. So the magnitude of the electric field is going to be constant. Only its direction is going to change, and it's always going to be in the radial direction. Now, if I draw my normal vector over here, I have to draw it this way, because remember, for a closed surface, by convention, we choose our normal vector to be outward. Right? A closed surface has an inside and an outside, and here it's going to be pointing outwards. So my electric field is going to be parallel to my normal vector, okay, everywhere. this was in radial direction at every point. Normal vector is obviously in radial direction at every point, which means that this dot product becomes a simple product. Because the two vectors are parallel to each other, remember this is the A n hat, and E is parallel to n hat, so it becomes a simple dot product, a simple product. Okay? E dA. And now I'm going to use something that I already mentioned, that the magnitude of the electric field, this thing here, has to be constant all over the sphere. As I move around the surface, my distance from the, well, actually nothing changes, right? Not just the distance from the charge distribution, but nothing in my problem changes. As I move along the surface, it remains the same problem. It's just I'm at a different point, but what I see is always the same. So this E must be constant as I move along the surface, which means I can take this out of the integral. Okay. And now the integral is trivial, right? I have an integral over some closed surface. These dA's are the little parts that, you know, form my surface. It doesn't matter what shape I choose for them. It really does not. This could be, you know, little triangles, something like little squares, whatever. But in the end, I'm looking at these little pieces of this Gaussian surface and I'm adding up, integrating over all of them. So this just gives 4 pi r squared. Okay. And this is equal to the enclosed charge divided by epsilon naught, which means that the electric field as a function of r is going to be Q enclosed divided by 4 pi epsilon naught r squared, which is the same as the electric field of a point charge, right? And this is something you might be familiar with, the Newton's theorem from gravitational field, that if you have a spherical mass distribution, it acts like a point mass at its center. Same thing would for a spherical charge distribution. With respect to outside, the spherical charge distribution is going to look like a point charge at its symmetry center. With respect to outside, this is important. Now what if this is inside? What if I choose a point that's inside? Okay. My strategy is the same. I still want to have, you know, some simple properties for this electric field. I still want to be able to, you know, get this dot product easily and so on and so forth. So so let's call this r prime. I'm going to choose a sphere of radius r prime. Now the same arguments apply. Okay, the electric field should be in radial direction. Okay, so this dot product becomes a simple product. It could be inwards or outwards, right? It's not so easy to make an argument for the inside of the sphere. The reason is going to become apparent in a moment. And so I'll just, you know, I can keep a plus minus sign over here. But the electric field magnitude, again, as I move on this inner sphere, the problem remains the same. The electric field magnitude should remain the same. I can take it out. So this step also carries over. And this step also carries over. I'm just adding up little pieces of this sphere. And their integral is going to be the surface area of the sphere, 4 pi r squared. The right-hand side is Q enclosed divided by epsilon naught, but now Q enclosed is 0. For the outer sphere, Q enclosed is Q. For the inner sphere, Q enclosed is 0. It has to be. So the electric field, so this is for R larger than R naught, whereas it's going to be 0 if R is smaller than R naught. Now at this point, inevitably someone wonders, what if R is equal to R naught? It's not a meaningful question. The electric field on top of a charge is not defined. It's just, as you know, infinite, so we're not going to deal with that question. Okay. Any questions about this procedure? Anything?
What happens if that sphere is not a product of an insulator?
It doesn't matter. If the charge distribution is spherical symmetric, It doesn't matter if it's a conductor or a insulator. If it's a conductor, it's automatically spherically symmetric.
Side is going to change.
It's not going to, no. If the charge distribution on the outside is spherically symmetric, then going from here to here to here to here, it's all valid. It's not going to change anything. Now, the question is asking, what if it's a solid sphere? Okay? Then having a conductor or an insulator is going to make a difference. Now for a conductor, but let me first make sure that I address your question fully. So if this was an insulator, meaning the charges would not be allowed to move on them, on this object, then this would not change anything as long as the charge distribution is spherically symmetric. Do you disagree?
No, I don't.
Okay. It's more fun if you disagree, but because this argument doesn't depend on whether the charges can move or not. In fact, this whole argument just assumes that the charges are static, they just sit where they are, and they're spherically symmetric. Without the spherical symmetry, I cannot say this E is constant, so I can take it out. I cannot say it has to be in radial direction, and so on and so forth. But as long as it's spherically symmetric, then nothing else is going to change. Okay, the last part of the question is saying, what if this was a conductor? Okay. Then how will it behave? Well, if this, a solid sphere. So if this is a conductor solid sphere and it has some Q on it, all the charges has to come to outside. Okay. Inside the conductor, you cannot have any charges. And in fact, you can use Gauss's law to show that this must be the case. Okay. First of all, there can't be an electric field inside the conductor. Let's agree on that. Let me create some space here. So if I have some conductor, it doesn't have to be spherical, it doesn't have to be anything, but let's say that I have some electric field that's present in the conductor. What would happen? That would lead to a separation of charges, right? The positive charges would feel a force this way, right? Positive charges would go along the electric field, negative charges would go opposite the electric field, and there will be some polarization inside the conductor, and this will immediately create a counter field. The polarization will create a counter field, and they will just cancel each other. Okay? So an electric field in steady state cannot live inside a conductor. Which means, if I take the sphere of radius r0, let's just do it again, and look inside to what's happening. Let's draw a hypothetical surface. So this hypothetical surface do not need to reside in vacuum. They can be inside materials, they can penetrate materials, doesn't really matter. But if I have this hypothetical Gaussian surface of radius r, then as I write this integral to calculate the electric flux, well, the electric field is 0. The electric field has to be 0 because of this argument in steady state, and we are looking at steady state. But the electric field is 0. The left-hand side of this equation, Gauss's law, is 0, which means the right-hand side has to be 0. So the enclosed charge always has to be 0. Okay? And it doesn't have to be a sphere that's centered, at the center of the sphere or anything like that. Okay? The electric field is identically 0. It's not 0 because of the dot product vanishing, or it's just 0. There is no symmetry argument here. So inside the conductor, there cannot be any free charges residing. All the charges should go to the surface. Okay? And once they go to the surface, there is going to be the spherical charge distribution. And that spherical charge distribution is going to act like a point charge. The electric field to the outside is going to be the same. The electric field inside is going to be 0. Now, if this was an insulator, if you were not just canceling the electric field this way, and the charge was uniformly distributed, then we would need to calculate the charge enclosed by this hypothetical surface. And I believe, in fact, that is the next example. Yeah, solid sphere of charge. So this is example 4 in this chapter. And they're saying an electric charge Q is distributed uniform throughout the non-conducting sphere of radius R0. Right? So you will need to calculate for this surface the charge that's enclosed inside, and let's do that. So Q enclosed here is going to be the total charge times the volume of this sphere that we are considering. So that's 4/3 pi r cube divided by the total volume. That's 4/3 pi r naught cube. And 4/3 pi will cancel. We're going to get q times r cube divided by r naught cube. So this is a trick that you're going to pick up if you solve a couple of examples. But it's the charge enclosed is going to be proportional to the cube of the radius. If this was a surface, and if you were like looking at a circular region, then it will go as the radius square circle. This is three-dimensional, so it goes as the cube of the radius of the sphere that you're taking. And if this is your Q enclosed, you just go ahead and plug this in over here. So inside, you're going to have some funny distribution. So r squared is going to cancel part of r cube. The electric field is going to be linearly proportional to r. To the outside, Q enclosed is just Q. You don't have this proportionality factors coming out. So to the outside, it's still going to look like this. But to the inside, the Q enclosed has to be replaced by this expression, and it's going to be linearly proportional to r, not inversely proportional to r squared. So it's going to look like this. Again, something you might have seen when you were studying gravity. And if you have a homogeneous sphere, and if you look at the gravitational field inside this, it looks like this. And increasing and then decreasing as 1 over r squared. I'm going to pick up from this example next time. But in the meantime, I think it's very useful if you look at this yourselves. Not just this one, but example 5 and 6, and 7, whatever. I don't know if I'm going to solve all of them. There's some repetition here. So I also put up the videos for the suggested problems for this section, for this chapter. So also take a look at them. And if you have questions, we are going to discuss them on Friday. But if you don't have questions, then I'm just going to move on to the next chapter. This is partially because I really don't know what to do, and also then we can save some time. And I'm sure you are going to have questions when the exam time comes, so I'm going to have some spare time to answer those live.